This video is a video about calorimetry calculations where some objects give up energy and other objects receive energy, and there's a temperature change to a final equilibrium value as these objects are in thermal contact. So I start here with an aluminum cup of 60 grams, water in this cup of 50 grams at 20 degrees Celsius. What's the temperature of the aluminum cup at the start of this problem? Well, you can assume it's 20 degrees Celsius, that this water's been sitting in the aluminum cup long enough that the temperatures have become the same. They're in thermal contact with each other. So the aluminum cup also at 20 degrees Celsius. We're going to drop into this water lead of 200 grams that has a temperature of 300 degrees Celsius. And we're not going to drop any ice into the system. We will need to use Q equals mc delta T to describe the energy that leaves the lead and describe the energy that's received by the water and by the aluminum cup. So these energies will add to zero. The Q for the lead will be a negative number. The Q for the aluminum cup and the water will be positive. So we write mc delta T first for the lead. 200 grams becomes 0.2 kilograms. We do this because our specific heat is given in joules per kilogram. So I don't want to multiply out here by grams. So 0.2 times 128 and TF minus 300. This is the delta T calculation. The final temperature is unknown. We'd like to find that. For the water, again, converting grams to kilograms. Specific heat for water, 4186. Delta T for the water, final temperature minus 20 Celsius. And then the aluminum cup, 60 grams becomes 0.06 kilograms. Its specific heat is 900 joules per calorie degrees Celsius, and the delta T. So in doing the calculation, 0.2 times 128, that creates a number out in front of this parentheses. I distribute that number, that's 25.6, on TF, and I also multiply it by minus 300. So these first two terms, that's coming from Q equals mc delta T for the lead. Then the water, likewise, creates two terms, and the aluminum cup creates two terms. I have like terms with the TF, so I add the 25.6, the 209.3, and the 54. Hopefully it's 288.9. You should check this with your calculator. And then I gather together the numbers, minus 7680, minus 4186, minus 1080, and I get minus 12946. Add 129046 to both sides, and we get an expression ready to be divided. We can calculate now the final temperature, 44.8 degrees Celsius. It's somewhat reasonable. It's in between the starting temperature of 20 that the water was at before the lead was dropped in, and it's not as high as 300. It's in between. And if this is the first of my calorimetry videos you're watching, there's another video that has a very similar problem, except ice is added to the water, and that was around 29 degrees Celsius if I remember. But this one, 44.8 degrees Celsius. Energy from the lead did not have to be used to melt the ice and then raise the temperature of that ice water. Here the energy from the lead is going into raising the temperature of the aluminum cup, and the water starting at 20 degrees Celsius. So ended up a little higher number than that previous problem. In these calorimetry problems, inspect the temperature. If you're going above a phase change point, then you need to use a little different approach in solving the problem. You'll have to stop, make the final temperature 100 degrees Celsius, see what energy has not been used by the lead, and then do the latent heat calculation, converting water to steam. We didn't have to do that here because we did not cross the phase change temperature from 20 degrees Celsius, where the water was originally, up to 44.8. We did not encounter either 0 degrees Celsius or 100 degrees Celsius in the temperature that the system moved through. So this calculation is legal. Be careful if you end up with a final temperature that would indicate the system is going across a phase change point. You'll have to use a little different technique of taking your energy supply from lead and using that to bring the system up to a phase change, and then the energy that's remaining in the lead would be used to calculate how many grams of steam you can make from the water. But do some practicing, ask your instructor some questions.